Welcome to today's webinar on the 10 properties of secure embedded systems. I'm Michael Ring, Regional Sales Director of Wind River Star Lab. And with me today is Michael Melberg, also of Wind River Star Lab. And today we're going to talk about what it means to secure an embedded system. We'll briefly touch on the threat landscape, kind of give you a sense of why we're mentioning the 10 properties. What are the threats against the system that you need to be concerned about? Then we'll jump into the 10 properties themselves that, they're not a 100% you have to do everything on the 10 properties. It's just common sense things that people like us who are security subject matter experts have come up with over the years for securing an embedded system. Again, we're talking embedded systems in this webinar today, not necessarily enterprise systems. But as you can see, a lot of the attacks we talk about, a lot of the threats and concerns now are also becoming applicable to enterprise systems or back-end systems too. And then after we talk about the 10 properties, we'll go into the Titanium Security Suite and talk about the product set that Wind River Star Lab has that may be applicable to covering some of the 10 properties. So the modern threat landscape is pretty tough. There have been a number of attacks, and these are not historical attacks that you see here in DroverRub, Blindside, and SolarWinds. These are actually attacks that have occurred recently within the last 12 months. So this is some of the most sophisticated attacks against systems and the kind of things that you, the owner of an embedded system, need to be thinking about. First is DroverRub. DroverRub is a Russian command and control malware. So it essentially is a Linux-based malware toolset that can be injected into a system. And once it makes its way into the system, it becomes stealthy. So it hides in the system. It sets up a command and control beachhead, which means it can start looking at the data and the applications in the system and deciding what it wants to transmit out of the system. Also included in DroverRub was a mechanism to exfiltrate that data using basically network traffic. So very sophisticated, very stealthy. It could be persistent in your system and you not even know about it, even with the most sophisticated of scanning or forensics tools. And basically exploit everything within your system because it's getting access to unencrypted data, applications, what you're doing on your system, what the system does. Next, we have Blindside. Blindside is the ability of an attacker to take over a system. So it uses a single known kernel vulnerability and allows the attacker to get access and then elevate their privileges up to admin or root access. And if you know and understand a Linux-based system, if you can get root access on a system, you pretty much have unfettered access and can do anything that you want to do on that system. So another extremely dangerous attack against your embedded system. And if you haven't heard about it, one of the most recent attacks and by far the most damaging, and it could be even more damaging once we find out the full details, is SolarWinds. And this was an attack where the adversary was able to take advantage of SolarWinds Orion update mechanism. They did so by using default set passwords to get into the certificate database. And they were able to sign code malware and attach it to updates. Well, as it turns out, SolarWinds had a customer set that included most critical government networks, a lot of industries such as Microsoft and Intel and others. So they were able to basically make malware look like it should be accepted within the system. Once they were on the system, similar to the other attacks that we mentioned, they were able to be very stealthy, hide themselves, move around and pivot within the system. And to this day, we don't know the full extent of what SolarWinds has done. And I imagine over the next several months, we're going to get a lot more details, but highly, highly sophisticated, extremely damaging to your system. Next slide. So with these three particular threats in mind, and looking at the history of attacks and vulnerabilities within the system, subject matter experts such as Star Lab, we came up with properties of an embedded system that you should consider for security. And so what we want to do is walk through some of these attacks. Again, I mentioned earlier, it's not the be all end all. These are some suggestions. But if you were to take each of these 10 properties seriously, you'd have a very secure system and would be a very good starting point for your security architecture and in your embedded system. So now Mike is going to run through each of these one by one.
All right, awesome. So we'll start with number one, which is data at rest protection. And when you think data at rest, think about information that's sitting on a disk, right? A hard disk, a solid state drive, basically non-volatile memory where your data is going to be stored. Maybe your applications will be stored in a typical PC, right? It's the applications and data that would start everything up and get running. If that information is not protected on disk, and specifically if it's not protected with cryptography, then you could be in real trouble. And that's because the attacker can gain access to that data and those applications, and they can read it with unfettered access. They can open it up with different reverse engineering tools. They can make modifications to the applications, and they can change the data and siphon data off the system any way they want. However, if you use data at rest protection, specifically cryptography, then that means that the information that's stored on the disk is very difficult to read and is protected against those types of attacks. You're going to get authentic data that can't be modified at rest. You're going to be sure that it's authentic when the applications get up and running, and you're protecting it against taking it off the system, because even if you take that encrypted information off the system, well, it doesn't matter because it's encrypted and impossible to read by the attacker. So number one is data at rest protection. This is really a first step in making sure that your applications and data that are stored on an embedded system are in fact protected. And then you can guarantee later that they're in fact authentic and unmodified. Number two is authenticated and secure boot. So if you have everything sitting on your system encrypted, that means it's protected while it's at rest. But at some point, you got to get the system up and running. And so the question becomes, how do you guarantee that the software that you get up and running on your embedded system is the software that you intend to have running on the system? How do you trust the software that you've deployed, that it hasn't been changed in the boot process such that you have some malicious code running once the entire embedded system is up and running? And to protect against that type of attack, things like boot kits and root kits you may have heard of, you need an authenticated and secure boot. You essentially want to make sure that as you boot up, you're checking your environment, you're making sure that you're not on a lab bench somewhere, that you are in fact running on the system that you intend to run on. Then from there, you extract your keys from some kind of a hardware root of trust, maybe a TPM, maybe an HSM, maybe an FPGA. It doesn't really matter where. That's going to depend on your threat vectors. But at some point, you need to pull those crypto keys out of the secure hardware so that you can authenticate the software load. You can make sure that the software that you're about to load up into the system is in fact the software that you deployed. And if your environment checks out and your software is authentic, then and only then will you pull those the decryption keys out of your hardware and decrypt and get everything up and running. And so what this guarantees is that from the state of rest, again, from point number, property number one, where we have everything encrypted at rest, now we authenticate it, we check our environment, and we migrate into a decrypted load that starts on the embedded system and gets your embedded system running. But we're sure that it's the applications and data that we intend to have running on the system and not a malicious payload. Number three is attack surface reduction. And what this means is taking away all of the unnecessary code from the system that you really just don't need to have running. So many distributions of Linux today, for example, have a tremendous amount of enterprise code in there that would allow Linux to do anything, run on almost any hardware, and perform any number of enterprise level functions. However, if you're deploying on, say, a small IoT device that has a very specific purpose, you don't need all of that enterprise functionality. And in fact, if you deploy all of that additional functionality that you're never going to use on your IoT device, then you have a larger attack surface. You have more bugs and vulnerabilities that the attacker can take advantage of, which is a problem because if they can take advantage of a bug or a vulnerability in another piece of code that you're not using, they could pivot and they could get access to the code and data that is sensitive that you're trying to protect. So the more that we can reduce the attack surface, the more that we can take out information, code from the system that we're deploying, code that we're not going to need to use on the system itself, the less bugs we're deploying, the less vulnerabilities we're deploying, and the harder it is for an attacker to mount any type of attack or expose any type of exploit. Number 4 is hardware resource partitioning. So with hardware resource partitioning, what we want to do is make sure that we are only running on the hardware that we intend to. And in fact, we are limiting the hardware that that our software is running on. So again, in an enterprise system, in many cases, say for virtualization, the hypervisor software just allows the applications and data to be in any memory bank, run on any processor, utilize any PCI Express card, just as an example. We don't want to do that because there may be applications on another processor that are running that we don't want this other application to have access to. We're trying to isolate the applications and the data from each other such that an exploit in one doesn't pivot over and allow an exploit in another. And so to do that, we can tie specific applications and data to one particular processor or maybe one or two processors. We can tie it to one memory bank. We can tie it to one PCI Express card. We can lock down, in other words, we can lock down the applications and the data to a particular specific set of hardware components on the system. And then for other applications and data, they'll utilize other specific hardware components and they're not allowed to overlap. And that prevents, again, it's just preventing attackers from exploiting one application, gaining access to the application and data, and then pivoting over and exploiting another application and data on your system, potentially one that's sensitive that you're trying to protect. Number 5 is implicitly distrusting other applications and other hardware components on the system and using secure communication. So we never want to assume that another application on the system is trusted unless we can verify that it is. We never want to assume that another piece of hardware that's trying to communicate with us is trusted unless we can verify that it is, preferably with encryption, right? Authentication, some sort of secure communication. We want to make sure that the applications, when they're communicating with each other on the system or on a system of systems, are protecting that information as it flows between applications, between hardware components, between different servers, that everything is encrypted such that if an attacker is sitting in the middle and sniffing all of that information, they're only seeing the encrypted data, which it doesn't matter. They won't be able to exploit that. We also want to check and verify that if another system is trying to communicate with us or another application is trying to access our memory space, that implicitly we distrust that application or that other server or that piece of hardware. We don't trust it until it can verify its authenticity, until it can verify that it is who we think it is. If we allow another system to communicate with us, there are also, and we don't authenticate that other system, then there are all sorts of attacks that they can mount by pretending to be somebody that they're not and gaining access to our applications and data. And then from there, again, pivoting from the application that they've exploited into other parts of other applications, other parts of memory, and extracting your sensitive data. So we want to make sure that we distrust other applications or hardware components or computer entire systems that are trying to communicate with us by authenticating them, by verifying their authenticity, and then setting up, establishing a secure communications channel so that anybody that's sitting in the middle won't be able to gain access to our sensitive applications and data. Number 6, least privilege and mandatory access control. So these are two interrelated concepts that I'll explain one at a time. So for least privilege, we want to only give applications and users and data the privileges that they need to have, and not the maximum level of privileges to access anything on the system. So if you've used Linux before, you're familiar, with the concept of root or administrative access, and how you don't really want to be running in administrative, you don't want to be running as root, because that could lead to all sorts of problems or accidents on the system where you destroy data or install something that shouldn't be installed. So least privilege means only giving an application or a user the level of privilege that they need on the system and no more. So if the application should only be accessing a certain folder full of information, then we only give it that privilege to access that, and we don't allow it to access other folders on the system. We don't give it anything more than it needs to do its job. Mandatory access control is related in that we're enforcing that, usually at the kernel level. We're making sure that the application is only accessing the data that it should access, and nothing more. We're making sure that if an application can only write to a certain directory or a certain file, that we enforce that, and that we don't allow the application to read from it because it doesn't have the privileges to do that. So the combination of these two, this least privilege and mandatory access control together, are basically enforcing how the applications and the data and the users interact with each other, and not giving them more access than is necessary to do their job, for fear of giving them too much access where they could potentially exploit an application or siphon off data that they shouldn't have access to. Number 7 is data input validation. We want to make sure that any data that's input into our system, whether at the command line with a keyboard, or remotely through a secure channel, is validated. We don't want to assume that the data that's coming in, that the inputs that the user or another application are providing are valid until we actually validate them. If we assume that they're valid and we don't validate them, then we get all sorts of different attacks and vulnerabilities that open themselves up to the attacker. So you may have heard of buffer overflow attacks, where the attacker is sending more information than the input buffer can handle. And what happens is that extra information, because we're not validating it, we're not validating the size of the buffer, we take in the input, and all of a sudden the attacker can get extra code executing on the system without our consent. And so those types of attacks are very problematic, and they're very easy for an attacker to do. So we want to make sure that any input that comes in, again, whether somebody is using their keyboard to enter data into the system, or in many cases, whether another system or another application is trying to communicate with us and they're sending us inputs, that we're validating the length, the format, and the content of that input before ever allowing it to be worked on or processed by the system itself. And this just prevents those types of buffer overflow attacks and a number of other sort of data input attacks that could lead to an attacker exploiting the system by sending us malicious code that we're not checking and allowing to run on the system, which again causes problems, because then they can gain access to one application and pivot and get access to other applications and data that they're not supposed to have access to. Number 8 is, this is a very simple one: secure software build and OS configuration. So when we build our applications, when we build up our operating systems, when we build up the system itself, there are many options that many times we don't even think about that are available to us that can protect the system. Some of them that we just mentioned, the buffer overflow attacks, right? There's flags and switches at the compiler level that you can turn on, which check for things like input errors, or input overflows or buffer overflows and things of that nature. And these switches are very easy to turn on, and they give you a lot of security benefit without a lot of cost. It's just a matter of turning on the available options at the command line or within your within your visual development interface, and making sure that those secure options are set. There's secure options at the compiler level. There's secure options at the operating system level. And all of these should be looked into because, again, they're very easy to turn on and they prevent a whole number of different attacks. In fact, we just wrote a blog post about the different operating system configuration, the Linux operating system configuration options that you can turn on to make your Linux distribution more secure. There's upwards of 50 different options that you can choose from, many of which cause zero or extremely low impact on the end distribution performance-wise, and they really cost you nothing in terms of time because you're just turning them on, and it's giving a much more secure system. So this is really important and very easy to do. Just make sure that you're configuring your software at build time, whether it's your applications or your operating system, configuring it for the most secure build by using those flags and those options that the compilers and the Linux distributions give you. Number 9, software containerization and isolation. So kind of very much like hardware resource partitioning that we talked about before, we can containerize and isolate software to make sure that code that's exploited in one application or one virtual machine doesn't leak over and exploit code in another application or another virtual machine. So there's different types of containerization and isolation technologies. One is containers themselves, right? Docker containers, things of that nature. While not inherently secure, they can provide a more secure boundary. And there are things you can do with the configuration to make those containers more secure. And virtualization, right? Putting your entire software stack, your operating system and your applications inside a virtual container can help mitigate different attacks, especially if you go the distance and ensure that those virtual machines or those containers are only able to access certain pieces of hardware in combination with our prior one of our prior 10 properties, which was the hardware resource partitioning. So this is just taking the software, installing it into some sort of container, whether virtual machine or a container itself, and isolating it from others so that an exploit that potentially gets into one application doesn't leak over, doesn't leak outside of that container, doesn't leak outside that virtual machine, and gain access to applications and data that are in another part of the system, that may be another container or another virtual machine. And the 10th and final property, this is integrity monitoring and auditing. You can't really take action if you don't know that your system is being attacked. And so once you're deployed, we want to constantly monitor the integrity of the system. And for cases where we're keeping logs, where we could check those logs later, we want to create, audit trails of the things that are happening on your system so that we can know when an application was updated or when a certain data was accessed. So between the two of these, if we're checking the system constantly to make sure that we're upholding its integrity and we're auditing the types of things that are happening on the system, then we're both guaranteeing at runtime after deployment that your system is in fact in good running state. And after the fact, you can come in with the auditing and you can check to make sure that your system hasn't been attacked or compromised in any way, that your system isn't being misused in any type of way. So these two things lend themselves to protecting your system after it's deployed, after you've configured your build environment and you've pushed it out the door into production, making sure that everything remains secure, that the integrity of the system remains intact, and that if later you come in, you can check it to make sure that nobody has been messing with it, and that no malicious code has been installed, and that the data and the applications are running the way that they're supposed to be running. All right, over to you, Michael.
Thanks, Mike. It is impressive to see that 10 properties in that list. Every time I see it, I'm fundamentally, I believe that if people that have embedded systems will address these 10 properties, they really will have a secure infrastructure. So now let's pivot for a second and talk about the kind of things that Wind River Star Lab can do to help. So our focus is on helping customers meet security requirements and produce a security architecture that will be consistent with the 10 properties. We do that in 3 phases. We address at rest. We make sure everything's encrypted. We support the secure boot process because the system has to start up. And then during runtime, whether you're in a virtualized environment or bare metal, we apply the security at that point to basically lock down the operating system and make sure that the system only does what you, the owner of the system, wants it to do and nothing more. And so we do that through licensable products. These are products that are available today. 2 products in our Titanium security suite. There's Titanium Linux, which is our operating system hardening for Linux, and our Titanium Secure Hypervisor, which is a Type 1 hypervisor for Intel, Broadwell or newer chipset with at least 4 cores. And then our secure boot is done through professional services. So let's walk through each of these and kind of give you a sense of what we're trying to accomplish. So with Titanium Linux, it's all about providing the at-rest protection, encryption, and the hardening of the runtime. So the mandatory access control to lock down the operating system at runtime. So that if applications are supposed to operate in a certain way, they do that, but they don't do anything else. One of our key points is we can't impact the functionality of your system. Your system still has to do what it was intended to do. But again, we want to make sure it does nothing more. And we do that through mandatory access control, through strong encryption at rest. And we make our configurations immutable. And by that, I mean, they can't be changed in the field. And that's important. You can set it up in your lab, in your depot environment, exactly how you want it to run. But once the system is deployed and your product goes in the field, you can't change the security configuration. And that's applicable even if you have root access to the system, you can't change that. So it really does take this wide open Linux distribution and make it very, very specific to what it needs to do. So functionality is not impacted, performance is within specification, and the tooling that we give you, including the training, is very straightforward. The product is very easy to use, and once you use it, you're just overlaps very nicely with the production process. So hardened Linux, securing any Linux instance, that can be Wind River Linux or any other distribution that is out there. Next, we have our Titanium Secure Hypervisor. I mentioned this was for Intel. If you need a solution for ARM devices, Wind River does have its Helix virtualization platform that would be an option there. But on the Intel side, we have a case where we can run our Type 1 hypervisor that's based on Zen. We can run it on, again, Intel, Broadwell, or newer chipsets with at least 4 cores. And again, we're a mission critical product. We're not a safety critical product. So we do mission critical by way of not allowing the oversubscription of cores and memory. So that means that each of your VMs is set up to be extremely performant so that within that VM, it appears as though you're running bare metal, and our performance data supports that. We have direct allocation of resources. And again, what we do is make it such that you can shrink the hardware footprint on your platform down to one board with multiple cores and enough memory, and have each of those operate extremely efficiently. Through separation and isolation, that's the security aspect of what we brought in. And again, that covers several of the 10 properties that Mike spoke about earlier. Next slide. And finally, there's our secure boot process. That is a professional services engagement. Some customers that we deal with already have a secure boot mechanism, so we can work to support that. Or if a customer doesn't have anything they're doing currently in the way of secure boot, we can use a number of different Intel-based solutions to come up with the process of receiving the key material that's stored in hardware once the hardware secure boot process has taken place, and securely receiving that key material so that we can kick off encrypted applications and allow access to data.
All right, so now with all of that in mind, the 10 properties, and with the two different products and professional services that we do in mind, wanted to cover quickly, how do those 10 properties map to the types of protections that we offer? And one really important thing that we haven't covered yet is a mindset shift. Mainly that most people think that they need to keep the attacker out of the system. But in fact, that can be an impossible task to do, right? Every time you deploy your software, your system, attackers are coming up with new tools, new technology, new techniques to gain access and to break in. Even if you deployed a system with 0 bugs and 0 vulnerabilities today, somebody is going to discover something in the future that gains them access to the system. So if you can't keep the attacker out, what do? Well, you have to assume that the attacker is already in. And so those 10 properties, those 10 fundamental properties of securing an embedded system, assume that the attacker is already in and still do what they can to protect the system. Using data at rest and secure boot, attack surface reduction, and all of the others that we covered, we can have an attacker inside the system with potentially root or administrative access and still protect our critical applications and data. And so each one of those products, Titanium Linux and Titanium Secure Hypervisor, and the secure boot services that we offer, cover one or more of those 10 properties. In fact, we cover 70% of all of them, 7 out of 10. So Titanium Linux, for example, protects your applications and data using data at rest. Our secure boot services, of course, cover the secure boot aspect, making sure that your system gets up and running and is in an unmodified, unmalicious state. Our Titanium Secure Hypervisor implements the principle of attack surface reduction, where we took the Xen hypervisor framework and we reduced the code size by 40%, just giving access to the functionality that's needed on a secure embedded system. Titanium Secure Hypervisor uses hardware resource partitioning and the principles of least privilege. Titanium Linux used the principle of least privilege and mandatory access control. And all of them follow these secure, secure build and configuration guidelines. And both of those products, Titanium Linux and Secure Hypervisor, utilize the concept of containers and isolation to prevent an exploit in one application or one virtual machine from extending over and accessing other applications and data or other virtual machines. So with this idea that the attacker is going to get in eventually and that we can't keep him or her out forever, we have to assume that the attacker is already in the system. And you can see here that the products that we offer for Secure Boot do in fact protect, again, 7 out of 10 of these 10 properties. And what about the other 3? Well, those are secure communications, data input validation, and integrity monitoring and auditing. And these are things that are very critical, but they're really IT best practices. These are things that you do at the IT level to establish secure communications between different systems by validating input that is moving between different systems. And then, of course, integrity monitoring and auditing happening at the system level after deployment. IT best practices that are very necessary for many types of systems that are deployed, but aren't things that you do, prior to deployment that you would do for these other 7 that we can do with these products here. So by covering all of these with the product sets that you see and with IT best practices, you're covering all 10 properties, and you're in a really good, more secure position than you ever would have been before, to try and not only keep the bad guys out, but assure that if the bad guys in fact get in, you still are protecting your critical applications and data against all sorts of different types of attacks.
Yeah, Mike, it's really critical that we get that mindset shift. We really do have to start assuming that the attacker is going to get into the system. So that's our webinar for today. We want to thank everyone for attending. As you can see, the threat landscape is serious. The threats are growing year over year. We introduced you to 3 particular threats in DroverHub, Blindside, and SolarWinds that are recent 2020 attacks that are extremely dangerous to embedded systems. Then we focused on introducing you to some properties of secure embedded systems, properties that subject matter experts like Starlab and Wind River agree that you should consider. Then we talked a little bit about our product set, our Titanium security suite, Titanium Linux, which is Linux hardening. We talked about the Titanium Secure Hypervisor, and then the professional services engagement for the secure boot process. And I think you can see that there's a really nice overlap between the product sets, the 10 properties, and the idea that we could still keep an attacker at bay, even if they're in the system and have root access. So if you want to schedule a follow-on deep dive on any of the products that you heard about today, or to hear more about the 10 properties, please reach out to us and we can schedule a side session.